Alrighty, lads and ladies, welcome back to Honors Calc 1. I want to talk about a handful of things today. Mostly we're going to be focused on USub, but I also want to talk a little bit about honors projects. We are getting close to the end of the term, which means these need to be done soon. So I want to lay out some clear deadlines. I haven't been given a day. Normally the department, we throw a little party and everybody gives their honors presentations. There's pizza and things like that. Unfortunately, we cannot do that this semester, due to COVID. And as far as I know, the honors committee has not set a fixed date for the honors projects, but I would like us to have our presentations ready. Let's see. Let's say. What's today? Today's the 5th. So I would like to set a date for the papers, a nice, clear, concrete date for the papers. And then the presentations we can do after the final. So you have a little bit more time to polish things up. So what's today, the 5th? And the 28th is the day of the final. The last day of class is the 23rd. So let's see, I'm struggling to say when you guys should have those. I definitely need them in time to grade them. And grades are going to be due. Grades due here, grades posted 5/4. So grades are going to be due by like the 3rd of May. So let's do it like this. I want you guys to have time to study for your final. So let's have the honors papers due on the 26th. That way you still have a few days between then and your final. Don't rush these, right? The idea is we should be working on them throughout the term. If you haven't put a lot of time into your paper yet, I would strongly advise that you do that like now. So your final is the 28th. And I'll have the honors papers due, let's say on the 23rd, right? That gives you the weekend and the full week leading up to the final. So it'll be the last day of class, and that way I can get those graded and back to you by the final. Let me go ahead and turn on my screen share. We'll get some of these things done. First, all right. 2311 section 0H1 lecture. And today is the 5th of April. Today we're going to formally cover substitution. Substitution rule. Section 5. But a little announcement. So your research paper are due on 4/23/20. That's the last day of class, and this is what we said in the syllabus and at the start of the term. So this makes the most sense, and it also gives you the weekend and a few days before your final off to prepare just for the final. And then the presentations. Usually, like I said, the honors committee gets together and decides on a day where everybody can come together. We order pizza and you guys can do your presentations all in a room with all the honors faculty and other honors students. And you can get to see what everybody else is doing. It's really cool. Since we are in the land of COVID, the honors presentations will have to be virtual. And I would like to do them after your final. That way it's a little bit lower pressure. So your final is on the 28th. But I'm aware that you guys also have other finals going on. So I want to ask you, Between the 29th and the 30th, which are the Thursday and Friday at the end of this month. Does anybody have a final that conflicts with doing these on the 30th? Or a reason why you would be unable to do them on the 30th? Okay, I'm not seeing any protest here. So I will go ahead and schedule our honors presentations for 4:30. And we'll say at 11 a.m. That's when our class meets. All right. Okay, yeah, go ahead and check. So I can be a little bit flexible here between like the 29th and the 30th. It does have to be before that following Monday because that's when grades are due. And of course, these are a part of your grade. We could move it earlier if we wanted to. We could do it on the same day of the final. We could do it on the 29th, which is the day after the final, the Thursday of that week, or we could do it on the Friday, which is the 30th, which is what I'm leaning towards now. And remember, along with these papers, sorry, along with the presentation, you need to have your poster board. Have the project board for the presentation. Okay, Thomas says he doesn't have any conflicts there. If you do discover that you have conflicts, you need to let me know immediately. And I'm going to set these as due dates. Specifically the research paper, this is a hard due date. You need to get them turned in by this day. If you're having a hard time with your research paper or anything like that, you want any sort of help, please email me, come to office hours, talk to me. These are a non-trivial chunk of the grade. Just to remind you, the grade breakdown is in here. So the honors project is 50 points, or about 8% of the grade altogether. So it's important that you get those done. So involved in here is the presentation, the poster board, and the paper. So all of those together are worth half of an exam grade, which is non-trivial. So please, if you need help with your paper, you're having a hard time, or you just want to bounce some ideas off of me, send me an email, Canvas message, come by office hours, any of those things, but do not put this off anymore. All right, if you have not gotten started on this, if you don't have a meaningful amount of work done on it yet, then you are behind. It's not the end of the world. This is just a gentle reminder to please, please, please get on this shit, because we're going to have these papers due on the 23rd of this month. And then the presentations will be on the 30th at 11 a.m. Remember how the presentations work. You can put together like a little slideshow or a little video, however you want to do it. And then we'll present through Zoom. Okay, just like your student teaching. And then along with the presentation, you need to have your poster project board. And I invite you, or encourage you to enter in the roof fair, which is like a big science fair. It's research on undergraduate education. So if you are proud of your honors project and you want to enter it into this little science fair competition type thing, I really encourage you to do so. There are prizes, there's scholarship money, there are networking opportunities, all sorts of really good things. Looks great on a resume, looks great on a transfer application. If you think you might like to enter in the roof fair, talk to me or talk to Bobby Hom or Eugenio Zalvadar. Those are the faculty on campus who I know that are connected with the roof fair. There are others if you know somebody else. But the easiest thing to do would be to talk to me, and then I can put you in touch with the necessary people and paperwork. All right, any questions or comments about what's due when or what you need to do? Remember, there are these three components, right? There's the research paper, There's the presentation, and there's the project board. So those are the kind of 3 things that you need to do to get that 50 points at the end here. Okay. So last Friday, we looked at a few examples of the substitution rule. We saw kind of how it works in 2 particular integrals. Today, I'm going to go ahead and give you the formal theorems, and then we will look and see exactly how to use them just through more examples. Your homework this week is just the one section, section 5.5. It's a fairly long homework set, but it's all use of, it's all substitution. Let's get into it. It's uploading now, Katie. So substitution in definite integrals looks like this. We say if u is equal to g of x, where g of x is differentiable, then the definite integral from a to b of f of g of x times g primed of x dx can be rewritten in terms of the variable u. Remember, this is like a backwards chain rule. This looks very much like the chain rule. And what this theorem tells us is that we can go ahead and evaluate that as a new definite integral in terms of the variable u, integral f of u du. But now it's going to be taken from g of a up to g of b. And believe it or not, this is the thing we did last time with that square root of x minus 1 and with the sine of 2 theta integral. So this is sort of the first theorem. And I'll go ahead and state the second one, which is very similar, just doesn't have any bounds. But you'll see that there are some subtle differences. So if you're looking at an indefinite integral, and you again have these hypotheses, if u is equal to g of x, where g is differentiable, then the indefinite integral of f of g of x dx, oh, sorry, f of g of x, sorry, integral f of g of x times g primed of x dx. This can also be rewritten as another indefinite integral, just integral f of u du. So they're really the same thing. It's just that the bottom one doesn't have any bounds. And I think it's easier to understand these in terms of definite integrals because it kind of helps us see what's going on a little better. But we'll get practice with both today. And we're going to begin, like we did with last time, playing with some definite integrals. There is a resource that I've added to your modules. See if we can find this over here. I posted it for my other section. Make sure I posted it for you guys also. Explaining a little bit why we have to change the bounds when we make a a substitution in a definite integral. And it's also going to help you understand a little bit what the various pieces in the substitutions are. Oh, no, we don't have it here, so I'll copy it over in a second. So you'll see a link in the modules at the very, very bottom to this page. And I would like it if you guys would read this page, specifically the explanation behind dx here. You may recall we talked about with that sine 2 theta substitution on Friday, how the substitution we made kind of cut all of the rectangles in half, right? It kind of squished the rectangles in half in terms of their widths. So the differential du was like 1/2 d theta, or 1/2 du was equal to d theta. That understanding of like cutting all of the widths in half works really well when the differential is a constant. But there are other instances where the differential term is not constant. And I'll show you some examples of those and remind you what they are. But I just want to say that reading this webpage and taking the time to look through everything here will help you understand what's going on with those. So we'll come back to that in a little bit. But before we get to the more challenging stuff, I want to just look at a few simpler examples. So kind of similar to one of the problems from last Friday, I'd like to evaluate the integral from 0 to 1 of the square root of 2x plus 1 dx. The difficulty here is sort of the same as the difficulty with the square root of x minus 1 integral from last time. The challenge is that I can't tell right away what an antiderivative for this function looks like. I can't apply my power rule. I can't do any of the things from my table, right? My known antiderivatives table, because this doesn't look like anything from my known antiderivatives table. And what's worse, I can't use any algebra to kind of split this up. There's no nice way to split this up. Specifically, the thing that a lot of people tend to want to do, a lot of people I see try to split this up as the square root of 2x plus the square root of 1. But this is sure as shit not an option, right? Powers never distribute like that. This never works. Powers don't distribute over addition or subtraction. It's just not the case. So I don't have any algebraic way to split this up into simpler pieces that I could then apply my known antiderivatives to, which kind of leaves me dead in the water. But I noticed that if instead of 2x plus 1 under the square root, I just had a single variable, like the square root of u, that sort of thing, I do know how to find an antiderivative for. If I'm able to get rid of this addition going on under here, then I will have something I can antiderive. So the move here is going to be to substitute for the inner function, which in this case is 2x plus 1. With the goal of turning this into a simpler function that I could then take the antiderivative of. Every time you do a substitution, the very first thing you need to do is you pick your substitution. You pick what you're going to sub for. And it's almost always going to be the inner of the functions, right? So you see like an inner function and an outer function. You always pretty much want to substitute for the inner. Now from here, you need to calculate the differential, du. Remember how this works? You just differentiate this thing and then write a dx at the end. So here, du is going to be the derivative of 2x plus 1, which is just 2 times dx. The other thing which we have to do is change our bounds.
The old bounds or old limits of integration were from 0 to 1. And these are x values. Remember, what we're doing here is we're finding the area underneath this function from x equals 0 to x equals 1. That's what the integral does. If I'm going to change my variable from x to u through this substitution, I need to figure out what values of u correspond to these old values for x. So I'll say my old lower bound was 0. So when x is equal to 0, what is u equal to? Well, to find that, I plug the old x value in here. When x is equal to 0, u is equal to 2 times 0 plus 1, which is 1. And when x is equal to my old upper bound, 1, u is equal to 2 times 1 plus 1, which is 2 plus 1, which is 3. And I always like to put this stuff in a little box here. It's just a convenient way to organize the information you're using for your substitution. Down here, I'll rewrite the original integral. I'll say, okay, so the integral from 0 to 1 of the square root of 2x plus 1 dx is equal to, and then I go through each of these little pieces and I start plugging in the corresponding bits for the new variable. So the integral from 0 to 1 becomes the integral from 1 to 3. Those are my new bounds. The square root of 2x plus 1 becomes the square root of u, because u is 2x plus 1. And then we come to the dx. It's very important that I replace this guy by his equivalent in terms of the new variable u. So I solve this for dx. This tells me 1/2 du is equal to dx, right? I multiply both sides here by 1/2, and I get 1/2 du is equal to dx. So the dx is 1/2 du. And remember, dx multiplies your integrand, so this is multiplying your integrand. This piece became this piece. That's how this works. And now we look at this as though it's an entirely new problem. It's totally fresh. Different variables, different bounds, different everything. But this one is easier than the original. Why? Well, this 1/2 here is a constant, and it's multiplying my integrand. So it can come out front. It is a constant multiple. And remember, that's one of our rules for integrals. Constant multiples pop out. So I have 1/2 integral 1 to 3 square root of u du. And if I gave you that problem, everybody would know what to do. We find an antiderivative for root u. That's going to come from the power rule. And then we evaluate between these bounds. So an antiderivative for the square root of u, we can think of this as integral 1 to 3 u to the 1/2 du, right? So when I come up with my antiderivative here, it will follow from the power rule. I'll just add 1 to this power and then divide by the new power. And when we take our antiderivative, that's when the integral symbol and the du go away. The 1/2 comes along for the ride. If I add 1 to that power, that becomes u to the 3/2. And then I need to divide by that new power. And all of this gets evaluated from 1 to 3. Okay, so pay attention to the steps. I didn't do any calculus here to here. I just rewrote the square root of u as u to the 1/2. And then from here to here, I took an antiderivative. When we take the antiderivative, the integral symbol and the du go away. Now in here, there's some algebra I can do to clean things up. When you divide by 3/2, that's the same as multiplying by 2/3. So I get 1/2 times bracket 2/3 u to the 3/2, all evaluated from 1 to 3. Now I go ahead and do the evaluation. That's 1/2 times 2/3, 3 to the 3/2, minus 2/3, 1 to the 3/2. 3 to the 3/2, that's the square root of 3 all cubed. Now the square root of 3 is a nasty irrational number, so this is not going to be nice. The 1 to the 3/2, though, that is nice. 1 raised to any power is 1. Or you can think of it as the square root of 1 cubed, which is 1 cubed, which is still 1. So this becomes 1/2. This piece, there's not much I can do with. It's just 2/3 times 3 to the 3/2. And this piece is just minus 2/3. And you may notice that we can factor out a 2/3. There's nothing wrong with doing that. So I'll get 1/2 times 2/3 bracket 3 to the 3/2 minus 1. And then you can cancel these 2's and you get 1/3 bracket 3 to the 3/2 minus 1, like so. If you wanted to stop here, that would be okay, especially on a test if you're worried about conserving time, but I wouldn't want you to stop here. The fact that this power simplifies really nicely, I want to see that you know that. And if this power simplified nicely, I would want to see that too. So this would be the place you could stop on a test and still get full credit if you're trying to be very careful about time management. Questions on this guy? Okay. So again, the trick with substitution, you got to start by picking what you're going to substitute for. And to do that, you want to look for the inner function. You want to think of your integrand as an inner and an outer and sub for the inner. Then right away, you calculate the differential. Remember the rule for calculating differentials? We talked about this way back in chapter 3. If say u is equal to f of x, then du is f primed of x times dx. That's how we calculate differentials. You just differentiate, but you write the dx on the right-hand side. Let's try another. There were a couple here in the book that I liked. Yeah, this is good. 1 to 2. So we have the integral from 1 to 2 of dx over 3 minus 5x quantity squared. There's a few things that you could do algebra-wise to help you see a little bit what's going on. First, I want to comment about the dx being upstairs here. Remember, the dx is always multiplying your integrand. So a dx up here is the same as a dx over here and a 1 up here. And I think a lot of people, myself included, find it a little bit nicer to look at if you write it that way. Again, we have a similar sort of issue as to what we had with the square root and the last guy, right? Is that this piece here, there's no nice way to split this up algebraically. You could FOIL out the bottom, but then you've got 1 over a bunch of stuff. And you know, fractions don't split up over their denominators like that. It's not like 1 over the first term plus 1 over the second term plus 1 over the third term. That doesn't work. What we could do is rewrite this as the integral from 1 to 2 of 3 minus 5x to the negative second power. And now I think it's a little bit easier to see sort of what's my inner function and what's my outer function. My inner is this 3 minus 5x, and my outer is the negative second power. So I want to substitute for the inner function. I'm going to substitute u equals 3 minus 5x, which means du, the differential, 3 differentiates to 0, and the minus 5x differentiates to minus 5. So du is minus 5 times dx. I'm also going to change my bounds. Every time you substitute in a definite integral, you need to change bounds. And I think especially many of you have seen this before in high school or elsewhere. You may have been taught that you don't need to do this. That's bullshit. You do need to do this. It's not optional. Yes, there are workarounds, but they're shitty. They're bad. Don't do them. Every time you make a substitution in a definite integral, you need to change your bounds. So when x is equal to 1, what will u be equal to? Well, if I come back here and I plug 1 in for x, then u would be 3 minus 5, which is negative 2. And when x is equal to 2, my old upper bound, u would be equal to 3 minus 5 times 2. Well, 5 times 2 is 10, so that's 3 minus 10, that's negative 7. So this is what's called an orientation reversing substitution. I'll explain why. Basically, your upper and lower bounds are no longer the larger and smaller guy. While we're here, we can solve this for dx. So this means negative 1/5 du is equal to dx. I look back at my integral and I start replacing the pieces. Integral from 1 to 2 becomes the integral from negative 2 to negative 7. And it's important that the old lower bound is what gives you the new lower bound. The old upper bound is what gives you the new upper bound. So this is now integral negative 2 to negative 7, even though negative 2 is the bigger one. And that's what I mean by orientation reversing. 3 minus 5x to the negative 2 is now just u to the negative 2. And dx is negative 1/5 du. And again, remember these are multiplied. So use good notation here. If you just wrote negative 1/5 du, it would look like those are being subtracted. So use the parentheses, use the dot, make it very, very clear when things are being multiplied, especially if they're negative, so it doesn't look like they're being subtracted. As in the previous problem, I can shuffle this negative 1/5 out front. Everything here is multiplication. So this is negative 1/5 integral negative 2 to negative 7. And inside here, I just have u to the negative 2 du. I can lose these parentheses here because this is just one variable being raised to that power. There's nothing more complicated going on inside. And that was sort of the goal. Remember, right? I substituted for the inner function so that I could have an easier time seeing an antiderivative. The challenge was that the power didn't distribute. Usually when we write an integral, it's nice to have the thing on the bottom here being smaller than the thing on the top here. But -7 actually sits way to the left of -2 on the number line. -2 is bigger than -7. And there's a rule that will let me flip these over. You know, the integral from a to b of f of x dx is the negative of the integral from b to a of f of x dx. It's not necessary, but it is a nice thing to do. So I can flip these bounds over, and that will sort of soak up this negative. Or you could think of it as spitting out another negative that will cancel with this negative. So I get positive 1/5 integral -7 to -2 u to the -2 du. Questions so far? All right, so we're ready for our antiderivative. This again comes from the power rule. If you add 1 to this power, you get u to the -1. And then if you divide by a -1, that's the same as multiplying by -1. So we can just think of it as negative u to the -1. And this is evaluated from -7 to -2. This is the same as -1 over u. And now we can go ahead and plug those bounds in. So if I plug in -2 for u, I get -1 over -2. That's positive 1/2. And there's the minus from the evaluation. And then if I plug in -7 here, you get -1 over -7. That's positive 1/7. So you have minus positive 1/7. If we have a common denominator between these, that is 14. This would be 7/14 minus 2/14, which is 5/14. So this is 1/5 times bracket 5 over 14, and the 5s cancel. And you get 1/14. Questions on this guy? Nothing too crazy, right? Nothing too crazy. Now, these problems are easy if your differential is a constant, right? If the thing you're substituting for has a constant derivative, then you can always solve nice and neatly for dx. It'll always just give you this constant factor, and that constant factor can always be shuffled out front. The problems get more interesting when you substitute for things that do not have constant derivatives. And that's where, again, that page I was talking about over here can really help you understand what's going on. If the thing you're substituting for doesn't have a constant derivative, then you're not just smishing everything by like 1/2 or 1/5. You're not just cutting the widths of the rectangles down by a constant factor. You're cutting the widths of the rectangles down by a variable factor. which means maybe over here near 0, it smushes the rectangles, but maybe over here near 3 or 4, it stretches the rectangles. Having a variable differential term in a substitution can be thought of as stretching and squishing the x-axis by different amounts in different places. And that's what you see illustrated right here. They're making the substitution u equals x squared. We know what x squared does. If you feed x squared a big number, it stretches, right? It gets bigger. If you feed x squared a small number like 1/2, 1/2 squared is 1/4, it gets smaller. So the substitution u equals x squared between 0 and 1 actually compresses things. And for everything bigger than 1, it stretches things. So just like having du equal to 1/2 cuts all the rectangles in half, having du equal to 2x dx, or having du equal to x squared, that's going to stretch and squish those rectangles by different amounts depending on where you are. And that can be a little bit intimidating to think of graphically, but it's not too bad to work with algebraically. These are called coordinate transforms. The piece that we're playing with here, the du piece, is what in a slightly more grown-up math class we would call the Jacobian matrix, or the Jacobian determinant. It's the piece that tells you how your change of variables affects the input space. The kind of simplest example I can think of here is something like this. Okay. Again, it's not obvious what the antiderivative is right away. I have no idea what the antiderivative for the natural log of x is, and that's actually not something we'll learn until we get to Calc 2. That's something that requires integration by parts. So without this x downstairs, we would actually be in a lot of trouble. Just the integral of this thing is quite tricky. However, because we do have that x downstairs, there is a way to evaluate this guy using substitution. And in order to make that substitution a little bit easier to spot, I'm going to rewrite this as the integral from 1 to e ln x times 1 over x dx. And I'd like you to compare that to the statement of the theorem here. Specifically, try to match up pieces here. So remember, we want to substitute for the inner function here, right? We're substituting u equals g of x, where u is the inner function, where g of x is the inner function. We need the derivative of the thing we're substituting for, or at least something close to that hanging around here. So what I see is ln x times its derivative dx, which hints that my inner is actually ln of x. So in other words, the outer function here is the identity function, but the inner function is the natural log. I want to turn this into the integral of just plain old u, and I claim that that is doable. If u is ln of x, then du is 1 over x dx. That's my differential. And that's very nice because I have precisely 1 over x dx chilling right here. The other thing I need to do, of course, is change the bounds. So when x is equal to 1, what is u? Who can help me out here?
Should be 0.
Yeah, very good. It's the natural log of 1, right? You just feed that old x value in here, and the natural log of 1 is 0. Similarly, when x is equal to e, we get that u is equal to, well, it's going to be the natural log of e. What's that?
1.
1. Very good. So under this substitution, this integral becomes, I'll rewrite it down here, integral 1 to e, ln of x times 1 over x dx. This will become the integral from 0 to 1 of ln x, well, that's u, times 1 over x dx. Check it out. That's exactly du. Right? 1 over x dx here, 1 over x dx here. This guy tells me that 1 over x dx is du. So that 1 over x dx is du. It's not always going to be this nice. In fact, most of the time, it's not going to be this nice. But if you're very, very lucky, the derivative of the thing you're trying to substitute for will be floating around in your integrand somewhere, and you can group it with the dx. So by grouping this 1 over x, this x downstairs, by writing that as 1 over x times dx, I'm able to see immediately my du. And now I just have to integrate 0 to 1 u du. Well, the integral from 0 to 1 of u du, that's easy. The antiderivative for u is just 1/2 u squared. So I evaluate that from 0 to 1. That's 1/2 times 1 squared minus 1/2 times 0 squared, which is just 1/2. Easy peasy. So this integral that at the start looked quite hard, through a very simple substitution, turned into a super trivial integral, right? Just the integral of u du. We could have done that several weeks ago. And the trick is spotting the substitution. So I want to look at some more problems like this, where your differential isn't a constant. Maybe we can take a look at one more definite integral example here. Good stuff like this. No, we haven't set the exact date for exam 3 yet. No, remind me though, we can talk about that. Let's try. Sound too easy. Yeah, how about that? Integral 0 to 1 x e to the negative x squared dx. So exam 3 is going to come after we finish section 6.1. Section 6.1 is the next section after 5.5. So I want to take our time on 5.5. Today and Wednesday will be all 5.5 problems. Friday, I'll introduce 6.1. And then next week, I'll probably put out the study guide for exam 3. So exam 3 is usually on like the last day of class or somewhere thereabouts. We might have it a little bit earlier. But yeah, so exam 3 will maybe be week after next, something like that, which I believe is the last week of class. All right, so new problem. I want to evaluate the integral from 0 to 1 of x times e to the negative x squared dx. And again, I need to think of this as like an inner and an outer. And I need to hope that the derivative of my inner function or something close to it is hanging out nearby. What is the inner here? If I have to look at this, kind of what would I like to replace by a single component if I could? So we've got a few ideas, some coming in through direct messages, some in the general chat. Everybody seems to be in agreement that it's something to do with this piece. Now, I wouldn't want to substitute for e to the negative x squared, that whole thing, for a few reasons. First, its derivative is quite complicated, and so the differential would be quite complicated, but something to do with this piece. And really what I would like is if this was just e to the x instead of e to the negative x squared, if this was just e to the u, yeah, that would be nice. So the move here is going to be to sub for negative x squared. And then du would be negative 2x dx. And I'll also change my bounds. When x is equal to 0, u would be equal to the negative of 0 squared. Well, 0 squared is 0. The negative of that is still 0. So the lower bound is still 0. And when x is equal to 1, u would be the negative of 1 squared. Well, 1 squared is 1. The negative of that is negative 1. So this new upper bound is going to be negative 1. So again, we have an orientation reversing substitution. And if we go ahead and start plugging things in here, I'm going to show you a different way to sort of think about this. What I did in the past problem is how I like to think about these things. You try to find your differential hiding in the original, you group it over here, and then you can just swap it in. But what most students do when they first learn this is they solve this for dx. So I would say, okay, 1 over negative 2x du is equal to dx. Make sure you write these in separate lines if you're going to do it like this. And now we start trying to plug things in. So old lower bound is 0, new lower bound is 0, old upper bound is 1, new upper bound is negative 1. So I have now integral 0 to negative 1. This x, I don't quite know what to do with, so I'll just leave him alone for the time being. E to the negative x squared is going to be e to the u. And then dx is 1 over negative 2x du, or negative 1 over 2x du, like this. And the miracle here is that the x's cancel. This fella and this fella cancel. So you get integral 0 to negative 1 e to the u times negative 1/2 du. And that's what you need. You need the x's to cancel. You need all of your old variable stuff to go away. We could have done the past one like this also. If I solve this for dx, I get x du equals dx, the 1 over x, and the x would cancel. So a note, comment here. We need every instance of the old variable gone. before we can do anything. Before we can do jack shit about the integral. And I mean like before we can take antiderivatives, before we can pop constants out, before we can split up algebraically, before we can do anything. After you make a substitution, you must get rid of every instance of the old variable. You cannot have u's and x's, cannot have du's and dx's, cannot have x's and du's, cannot have any permutation of that shit. Notice the bounds are now u values. The integrand is now a function of u, and the differential only has u's in it. No x's. We need all the x's gone. Insert your favorite joke about your ex-girlfriend, boyfriend, whatever. All the x's gotta go before we can do anything else. Every single instance of the old variable must be gone before we can do anything with the integral. And here that happened. All the instances of the old variable are gone. There are no more x's floating around. I can pop out that -1/2. I'm left with integral 0 to -1 e to the u du. Again, here I've got that weird thing where my upper bound is smaller than my lower bound, right? Like -1 sits to the left of 0 on the number line. So I'd like to flip those over, and that will soak up this negative right here. Same thing we did on that earlier problem. So this will become +1/2 integral -1 to 0 e to the u du. An antiderivative for e to the u is just e to the u. And we can plug in. So this is 1/2 times e to the 0 minus e to the -1. And e to the 0 is 1. So this is 1/2 times 1 minus e to the -1 is 1 over e. Okay. Questions on this guy? Yeah, oh yeah. Yep. Yeah, we would leave it like this. This is good. Okay. If we're all feeling super duper comfy, then I'll go ahead and look at some indefinite integrals, and then I'll let you guys go. The indefinite integrals here are honestly a little bit easier. It's the same sort of thing, just no bounds. All right, just that's it. So let's look at a couple of examples of indefinite integrals. We'll start simple. How about the integral of x cos x squared dx? What I see is that with the cos of x squared, at least, there's a clear inner and outer. All right, the cosine is the outer, the x squared is the inner, and that this x right here is very similar to the derivative of this inner. So all of that points me towards substituting for x squared. Which means du would be 2x dx. And since this is an indefinite integral, there are no bounds. So there are no bounds to change. I don't have to worry about that. If I take this du equals 2x dx and I solve it for dx, I get 1 over 2x times du is equal to dx. And then if I start plugging things into the integral, I'll leave this x for now. I don't really know what he's about. But cos of x squared, that's definitely cos u. And dx is 1 over 2x times du. And as they did in that last problem, these x's here are going to cancel. I can pop out the 1/2, and I get 1/2 integral of cos u du. And remember, an indefinite integral, the answer here should be an infinite family of functions. We want all the antiderivatives. So after we find our antiderivative, we'll slap on a plus c. An antiderivative for cos u, who differentiates to cos u? Well, that's just sine of u. So this is 1/2 sine of u plus c. And we would be tempted to call it a day there. However, the original question said, find me all the antiderivatives of x cos x squared. And if we come back to somebody who says that and we say, oh, it's 1/2 sine u, they would be like, what the fuck are you even talking about? Because they asked us a question about x's and we're giving an answer in terms of the variable u. So for indefinite integrals, not for definite integrals, just for indefinite integrals, at the end, you plug back in for u. So this would be 1/2 sine of x squared plus c. Nope. For indefinite integrals only, we plug back in for the variable u. And we do that at the very end. Right, you don't do that after you're making your substitution and here plug back in for, x squared and leave this as du. That shit wouldn't make sense. So for indefinite integrals and only indefinite integrals, after you've found your antiderivative and written your plus c, once you get to the stage at the very, very end, you plug back in u equals x squared or u equals whatever you made the substitution to be. And this would be your answer. You can always check an indefinite integral by differentiating. If you're uncertain, remember Ben taught us that. If you're not 100% sure that you did this correct, take the derivative. You should get x times the cos of x squared. And you will, by the chain rule here, you will. Rather than doing that explicitly for you, I'd like to work one last example and then I'll let you guys go. This time, we're going to look at the integral of e to the x over 1 plus, let's do it like this, e to the 2x dx. I like this problem a lot because it's not entirely obvious what is an inner and what is an outer. And there's an algebra rule for exponents that will help us see what our inners and outers are here. Does anybody see a part of this integral where I could apply this rule?
E to the 2x.
Yeah, down here, right? E to the 2x is the same as So upstairs I still have e to the x. Downstairs here, this is the same as e to the x all squared dx. Like this. And now we can ask again, do we see an inner and an outer? Or do we see an inner?
E to the x could be the inner.
Yeah, I think this looks like e to the x is the inner down here, right? Now there's a question about what about this guy? So is my outer like u over 1 plus u squared, or is it something else? And this is where I would say, all right, I know I want to substitute u equals e to the x. So I would rewrite this like this. Because if I'm going to substitute u equals e to the x for this inner, I know that the derivative of e to the x is e to the x. So I'm going to need an e to the x that I can put over here with dx for that differential. If I'm subbing u equals e to the x, then that means du is e to the x dx. And I'm thinking ahead when I write this e to the x down here instead of up here. I wouldn't want to write this as u over 1 plus u squared, because then I won't know what to do with this thing. Right? It can be a little bit harder to see what to do with this. So think about the differential when you make your substitution and see if there's a way to rewrite your integrand to help you figure out what to do with the du. The differential term is everything in substitution. Now there's no need to solve for dx or anything. I just see right away that this piece is du. So this is integral 1 over 1 plus u squared du. My du is e to the x dx. That's why I wrote him down there. Now, if you make the mistake of writing this as u over 1 plus u squared, and then writing here a du over e to the x, you're not dead in the water. There are ways to get where we need to go from there. You'd have to take your du over e to the x and recognize it as du over u, because u is e to the x. But it's a little bit harder to spot if you make that jump without thinking about it. Questions about how we get here? Okay, ideas about where we go from here. What is an antiderivative for 1 over 1 plus u squared? What does this look like the derivative of? Not tangent, but related to tangent. Yeah, arctan, or the inverse tangent. Remember, the derivative of tangent is secant squared. But the derivative of the inverse tangent of u is 1 over 1 plus u squared. So yeah, this is the inverse tangent, or you could write it as arctangent of u. And then we write our plus c at this stage because it's an indefinite integral. And we've taken our antiderivative. And then finally, they asked us about x's. We give them u's. We need to go back to x's because it's, again, an indefinite integral. So this is the inverse tangent of e to the x plus a constant. You have 1 or 2 problems in your homework that require a sort of clever substitution into an arctan thing. So if you are having a hard time spotting the substitution on any of those problems that kind of have this sort of shape, like something over 1 plus something else squared, take a look at a substitution like this. See if you can turn it into an arctan thing. Alrighty, that's all I've got for you guys today. Remember, your honors projects are coming due soon. I need the papers by the 23rd. The presentations will be on the 30th at 11 a.m., which is a couple days after your final. So just be mindful that that stuff is coming up, and so you need to be putting time into it. I want these papers and presentations to be good. You guys should be proud of them. They're what makes this class special. Is you get to take a slightly deeper dive into something cool. A few of you have come to me to talk about things, ask for a little help, or talk about papers that you've read. Some people I haven't really heard much from. So please, if you're at all stuck or concerned or anything like that, come talk to me. I'm happy to help you research it. These will be genuinely getting graded. It's not just like everybody gets 100. So you want to put some real time and real thought into it. Alrighty, that's it for me. I will see you guys on Wednesday, or if you want to come by office hours, I'll see you in a few minutes. Take care.